All right, so today, nothing new. We're going to get some practice solving quadratic equations, some good practice. But really the topic is not anything new. It's going to be about strategy, right? It's going to be about how do we find equation, because that's what we want to do. We want to solve them in the most efficient, quick, easy way. So there's kind of a little menu we can run through here, and we're solving a quadratic equation. So if the equation is in this form, right, the quantity ax plus b squared equals c. Now that's almost a little bit misleading. What's important about that? What's important about that form? Yes. So if the equation, if it's an equation where I can point to a single x, then what am I going to do? I'm going to use inverse operations in the square root property to isolate the variable. That's the quickest and easiest way to do it. Okay? The alternatives are all much more cumbersome and time consuming, and you're more likely to make mistakes. So there's step one. If we can point to a single x, always take advantage of our ability to just isolate the variable. Okay, if we cannot do that, then we have to put the standard form. Well, if we can find magic numbers easily, right? And we don't want to, if they're possible, that's not really the criterion for us. It's not if it's possible to find magic numbers. If it's simple to find magic numbers, then we find them and use the zero product property, right? If it's not simple, then we skip factoring and we move on down the list. Okay, if in our quadratic equation in standard form, if a is equal to 1, so the coefficient of x squared is 1, and b is even, you have the option of solving by easy to do. And I know completing the square is a real pain, and or b is not even, right? Because then when you take half of b to find your double magic numbers, if b is not even, you get fractions, and no one wants that, right? So if, however, a is 1 and b is even, you have the option of just quickly completing the square, which I think honestly is a really quick and easy way to do it. Up to you. It's optional. Your ace in the hole is what? If all else fails, how can you solve any quadratic equation? Quadratic formula. As long as you start in standard form, you can solve. What is a little bit cumbersome and inconvenient about the quadratic formula? You've practiced it now. What part of it is kind of a pain? Yeah, I mean, wouldn't you agree there's a fair amount of simplifying? You got square roots to deal with. Right. So it's, in certain instances, it's just easier not to have to go through all that rigmarole and just get to the solutions in a simpler way. But you can always do it. Sometimes it's just not the most convenient option. So what about one like this? Now this takes us back to radical equations. Quickly remind me, what's our strategy for solving an equation involving a radical? What do you do first? Well, what do you do even before that? What's your goal when you're solving an equation that has radicals in it? What do you do? Okay, good. You isolate the radical. Good. Done. Sides to whatever power we need to in order to undo the radical. So that means squaring both sides here, right? And then now remember, when I square the left side, that's a binomial, so I have to use my pattern to expand that out, or just FOIL it out, I guess. But we want to use a pattern. And then I'm going to put everything into standard form. Okay, so that gets us to here. Now, be the most efficient way to solve that quadratic equation. For sure. Yeah, I mean, we could complete the square. Because look, a is 1 and b is even, or I could use the quadratic formula. But if you can find simple magic numbers, that's far and away the easiest way to do it. What do the magic numbers have to multiply to? Positive 16 and add to negative 10. So what are they? There you go, negative 8 and negative 2. And this factor it. So what are my solutions? 8 and 2. There you go, right? Are we done? We're done with the quadratic, but remember where we started. Both valid, right? One or both might be. X equals 8. Does that work in my original equation? What do I get on the left side? 4. 8 minus 4 is 4 on the right side. Square root of 16. Is that true? That's true. Yeah. This one. What do I get on the left side if I evaluate when x is 2? Negative 2 equals square root of, true or false? Square root of 4 is what? 2. Yeah. So this is x. So I have to toss it. Only get one solution. Okay, make sense? Okay. First. Collect like terms? Yeah, okay, so on the left. Where am I going to push stuff, left or right? To the right, good. I want a positive. We push it to the right. What do you think here? Casey, what do you think? How would you solve that one?
You could just go with quadratic formula.
And probably you're going to do that, aren't you? Right. How come you just jump right to the quadratic formula on this one? Is factoring an option? Nope. No magic numbers exist, right? Why is completing the square a bad option? Yeah, because b is odd, right? B's not even. So we would just go right to the quadratic formula. And, you know, that's no big deal. You guys know we've had a lot of practice with that. A would be 1, B is negative 9, C is negative 6. So what do we get? What goes first? 9, good. Negative B is, in this case, positive 9. And then we're going to get negative 9 squared, which we could just turn that, I would just write 81, right? 81 minus 4 times what? Times 1 times negative 6. Okay, good. And on the bottom we get 2. So 81, and notice that subtracting a negative means I'm adding, right? So 81 or plus 24, what is that, 105? And 105, I get my discriminant is 105, so that's the number under the radical. Is that going to simplify? No, there's no perfect square factors of 105, are there, right? 105 is just 21 times 5, so the factors are 3, 7, and 5, no couples, right? So those are our two answers. Notice we get one for the plus sign and one for the minus sign. We get two solutions. Make sense? Okay. How about this one? Say it again. We are going to divide by 4. Let's do something else first. Say it again. Standard form. So push everything to the right. Good. And then dividing by 4 is right, isn't it? So we could factor out a GCF, which is it's a number, it's a constant. So I can just divide each side by 4. Do you even have to factor the 4 out? No, not really. You could probably just divide both sides by 4, and just jump right to the equation x squared minus 3x plus 1 equals 0, right? Okay, so how am I going to solve that quadratic equation? What are you going to do? Maren, what do you think? What would you do in that one? What technique would you use? I mean, can you find magic numbers? No, so we can't factor. Do I want to use completing the square? Probably not, right? Because A is 1, okay, good, but B is not even. It's odd, so I don't want to use completing the square. So what's left? Yeah, quadratic formula, right? We would just jump right to quadratic formula with this guy. Okay, and then what's A? 1. What's B? -3. And what's C? Yeah. Plug all that stuff in, and when the dust settles, I get underneath the radical, I get 9 minus 4, so I just get a 5. Stuck with a square root of 5. 2 solutions. Okay, make sense? Okay. Okay, how about this one? It's in standard form. Do we just jump right into like the quadratic formula? No, probably not. I agree. What should we do? What could we do?
Try to get common denominators.
Yeah, probably. So maybe clear fractions. How could I clear fractions here? What would I need to distribute through both sides of the equation? What number? 8. Yeah, right? The least common multiple of all the denominators. Okay, so if I good, so we could just multiply an 8 through. What's that going to give me? What do I get when I multiply the first term? There we go. When I multiply that first term by 8, what do I get? Okay, good. 5w to the 4th. How about the next term? Plus 8w squared. Last term. Minus 4. And then anything times 0 is 0, right? Okay? Okay, what's a little bit scary or inconvenient about that one? Okay, it's not quadratic yet, is it? Okay. How could I maybe turn this into a quadratic equation?
Substitution.
Yeah. What substitution would I want? What do I want to substitute for here? W squared. And take your pick, some other variable, right? How about if we just use x? So we could say something like x equals w squared. And then what do I end up with? Yeah, 5 times x squared plus what? 8x minus 4 equals 0. That looks better, right? Now I've got a traditional quadratic equation in standard form. Agreed? Okay. So I think they did this in slightly, they did the substitution first. That's fine, doesn't matter. And then they multiplied by 8. Okay. So we get a quadratic equation. Now how are we going to solve this one? Could just use quadratic formula. Okay, I mean, you could, but why would completing the square maybe not be a great option here? Yeah, because A is 5. I'm going to get a bunch of ugly fractions. So I'm going to cross that one off the list. Of course, it would work, but it's just too cumbersome. There is one other option. Quadratic formula, and you're fine just jumping to quadratic formula. Why might you be tempted to just say, just jump to the quadratic formula? I mean, when A is not equal to 1, factoring is a little bit tricky. But could you factor this? What would your magic numbers have to multiply to? Negative 20 and add to 8. So what would those numbers be? 10 and negative 2, right? So we really do have another option. Now, if you're good at factoring and you can do this pretty quickly, that might even be faster than the quadratic formula. It's up to you. So we could just choose the quadratic formula, but because we could find magic numbers that multiply to the outer product and add to the middle coefficient, we could do that. You already told me we'll split this into a positive 10x and a negative 2x. And so if I factor by grouping, then everybody agree I just take an x out of the first group, right? And so I know I'm going to have a 5x minus 2 in group 2, so I've got to factor out what, a 2? And so I end up with just x plus 2 times the quantity x plus 2 times the quantity 5x minus 2. Pretty quick, actually, isn't it? Right? If you can find those magic numbers, splitting and grouping goes pretty quickly. Or take your pick. A is 5, B is 8, C is negative 4. Just plug and chug in the quadratic formula. And I mean, there's just a little bit of computation there. 64 plus 80, that's 144, right? The discriminant's 144. Square root of 144 is 12. And so either way, I'm going to get two solutions. If I take the plus sign, what do I get? 4/10. If I take the minus sign, what do I get? Negative 20 over 10. And those are both going to simplify, aren't they? Right? So we get those two options. Either way, if I reduce those fractions or if I just apply the zero product property, right? Either way, I'm going to get the two solutions. X equals 2/5 or x equals negative 2. Agreed? Okay? But we're not done. We're actually not done. What do we still have to do? We got to reverse that substitution, don't we? Right? So we got to flip back to w's. So I actually end up with two equations here. I either get w squared equals 2/5 or w squared equals negative 2. Okay? So I'm not quite done. I got to solve for w. So what would I do to solve for w here? Yeah, use the square root property. So I get w equals what then? What? Square root of 2/5? Almost. Plus or minus, yep. Plus or minus the square root of 2/5, which I could split up. And then what rule am I breaking? Yeah, no tenths in the basement, right? Broke that rule. So what do I have to do to rationalize the denominator? Yeah, multiply top and bottom by square root of 5. And that's going to give me a 5 on the bottom and a square root of 10 on the top, right? How about the other side? If w squared equals negative 2, what's w? What are you going to get if I square root both sides here? Plus or minus? There you go. A negative inside a square root becomes? I outside. Yeah. Okay, so that's going to give me plus or minus square root of negative 2 gives me square root of positive 2 times I. So how many total solutions did I get? 4. Yeah, I got 4 solutions, didn't I? Yeah. Okay. Give me 1 to 5 on that. That all make sense? Okay. All right, so last couple examples. What about that first one? What could I do there, you think? Add 81 to the other side. Okay, let's see what happens. If I add 81 to the other side, p to the fourth equals 81. What do I get? I mean, how do I undo? I mean, interesting approach here. So let's try this out and see what happens. Could I just isolate p by using inverse operations? So first we added 81 to the other side. How would I undo a fourth power? I'd be a fourth root, and that's even, so I would maybe need a plus or minus. Okay, so then I would get p equals plus or minus the fourth root of 81. And what's that give me? What's fourth root of 81? 3, yeah. So I get p equals plus or minus 3. How many solutions did I get? 2. Does anybody think there's a possibility there could have been more? We haven't talked about this yet, but this is what we're going to talk about tomorrow. The fundamental theorem of algebra. It tells us that the degree of a polynomial equation tells you the number of complex solutions to that polynomial equation. What's the degree of that polynomial? 4. Okay, so the fundamental theorem is telling us that there are 4 complex solutions to that polynomial equation. Now it's possible, now that includes multiplicities, so it's possible that if you have like double magic numbers, for example, the same magic number shows up twice, that counts as a double solution. It actually counts as 2, even though it only shows up as one number. Okay, so maybe we missed something. We'll come back and take a second look at that one. Let's try the same thing here with this one. If I just try to solve for x directly, wouldn't I just get x cubed equals negative 27, and then I could undo that by cube rooting both sides? So x would just equal, if I take an odd root, I don't need a plus or minus. What is the cube root of negative 27? Yeah, negative 3. So I only got one solution. Okay. Again, how many complex solutions should I get for this one? Should get 3. I only got one real solution. Where'd the rest go? Okay, let's take another look at this. What if we don't isolate? What if we choose to factor this instead? Okay, so what pattern could I use to factor p to the fourth minus 81? Yeah, difference of squares, couldn't I? Because p to the fourth is what squared? Yeah, okay, good. So we could do it like this. We could call this p squared squared minus 9 squared equals 0. So what does that factor into then, everybody? P squared, yeah, I'll do p squared minus 9 times p squared plus 9 equals 0. Okay, give me 1 to 5 on that. Does that all make sense? Okay. If you wanted to, you could make a substitution there and say something like x equals p squared, right? And then that would have just looked like x squared minus 81. So it would have had x minus 9 times x plus 9. But then when we plug the p squareds back in, don't I just get that? Okay, again, give me 1 to 5 on that. How are we doing on that? I need to see feedback. You guys, how are we on this? Okay. All right, so, okay, now, look, I've got 2 separate factors there. I could just choose to use the zero product property now. What if I just took this one, for example, and I'm just going to set this equal to 0. So either p squared equals 9, or if I set this one equal to 0 through the zero product property, I get p squared equals negative 9. Okay, I could square root both. In both cases, I could just square root to solve. What are my 2 solutions I get from the green equation? Plus or minus 3. Or, what solutions did I get from the orange equation? If I square root both sides. P would equal plus or minus the square root of negative 9. Yeah, so P would equal plus or minus 3i. Everybody agree? How many total solutions did I get?
4.
Ah, okay. So what went wrong the first time? Well, what went wrong the first time is that you can't do this. You can't directly isolate a variable unless it's quadratic or smaller. Okay? You have to always factor until you get to a point where the factors are quadratic or smaller, and then I can just isolate directly. Okay? So there's a really important, and this is one of the most common misconceptions, I think, in Algebra 2 that's so pervasive. It shows up on the SAT tests and stuff. It's such a simple and avoidable one, too, if you just follow this one rule. When you're solving a polynomial equation, you must factor until you have quadratic or smaller factors. Then you can choose to keep factoring or not. You can just bail off the factor train and just solve those equations if you want to, right? Now notice the way we did this one. We're on the factoring train until the factors are quadratic or smaller. I could have factored that again into a difference of squares, p plus 3 times p minus 3, right? And then use the zero product property and gotten 3 and negative 3, but I chose to quit factoring and just set that factor equal to 0 and solve, right? Once you get factors that are quadratic or smaller, any factoring from that point forward is all optional. You can just set the factors equal to 0 and solve those quadratic equations. Okay, make sense? Okay, so then what went wrong with this one? What would I have to do here? Because that's cubic, I can't isolate x. What do I have to do first? I can't bail off the factoring train yet. Their factors are too big. What am I going to do with that? It's been a while. What pattern fits that? Yeah, that's going to be a sum of cubes, isn't it? Right? The sum of cubes pattern. Now remind me about the good old sum of cubes pattern. How does that one work? A cubed plus b cubed factors into what? A plus b times There you go. Remember that one? Turns out that one's pretty important. Yeah, so what's my A up here? What's my B? 3, okay, good. So then this is just going to factor into what? A plus B, x plus 3, times a squared minus x times 3 is 3x, plus b squared is 9. Right? Okay, so now by the zero product property, look what happens. I get either x equals negative 3, or this one is quadratic. It's not going to factor. Remember we talked about that earlier. When you use the sum or difference of cube patterns, that second trinomial is never going to be factorable, right? So this is one where we would just have to set it equal to 0, set that factor equal to 0 by the zero product property and solve some other way. How would I solve this one? Yeah, right, everybody agree? We know there are no magic numbers. B is odd, so we would just use the quadratic formula. And what would we get? X equals, everybody? 3 plus or minus square root of 9 minus 4 times 1 times 9. What's 4 times 9? 36, okay. All over 2, right? So I get 3 plus or minus square root of negative 27 over 2. And what's the square root of negative 27? Yeah, so I could break it into square root of 9, which is 3 times square root of 3, right? 3 outside, 3 inside. Negative inside becomes an I outside. And so I end up then with x equals 3 plus or minus 3 radical 3i all over 2. Now you could leave it like that, I think, in our assignments, but really it's better to split those up into separate real and imaginary parts. The best way to write this would be x equals 3/2 plus or minus 3 radical 3 over 2i. And then I get a total of 3 solutions. Notice that 2 of them are complex conjugate pairs, right? And that's all. Remember, that always happens. Complex solutions with imaginary parts always come in complex conjugate pairs. Give me thumbs. Are those complex conjugate pairs? Plus or minus 3i? Yeah. Because really, that's just 0 plus 3i and 0 minus 3i, isn't it? So that worked the same way. Okay, everybody good with that? Again, you can't bail off the factoring train until your factors are quadratic or smaller, right? Okay, jump in. You can work on this assignment a little bit. It's up there ready to